we've been talking this week about induction, doing proofs by induction. And my goal for today is to connect that idea very explicitly to programming in computer science. Because it turns out that doing mathematical proofs by induction and defining functions recursively, that is, defining functions in terms of themselves, are really two sides of the same coin. And recursion is a technique that we use all the time in computation, and proving things by induction goes hand in hand. So, so one thing is that, and I don't, maybe we've actually seen examples of this before, maybe not, I'm not sure, but it doesn't matter. We can define functions, let's say using recursion / induction. And there's a good reason for, I'm not choosing one of them because it's kind of both. And there's kind of different points of view to look at it. So basically, what this means is like define the function on some kind of initial values. Right, that's our base case. And then for define the function on other values in terms of its output on previous values. Okay, that's the general recipe. So let's see an example. So I'm going to make a function f from natural numbers to natural numbers, and I'm going to define it like this. f0 is 3, and f of n plus 1 is 2 times f of n plus 3. And I claim this is a perfectly valid way to define a function from natural numbers to natural numbers. So why is that? So why is this a valid definition of a function? And because not everything you write down where the function is defined in terms of itself, I mean, some of them might not actually be valid. And I can give an example of that in a second. But so the claim is f has a well-defined output for every input. Right? That's what it means for something to be a function. It has to give an output for every possible input. And we could prove this by induction. So in the base case, when n is 0, f0 is defined. That's just because, well, it just says right here what the definition of f0 is. So, because of the first clause, f0 equals 3. Okay, and then in the inductive step, let's we would say like let n be an arbitrary natural number, and suppose that fn is defined, right? So we'll suppose that f has a well-defined output for f of n. And then, well, that means f of n plus 1 is also defined. Why is that? Well, it's because of the second clause, right? The second clause defines f of n plus 1 in terms of f of n. So if we know that f of n is defined, then f of n plus 1 is also defined by the second clause, f of n plus 1 equals 2 f. Okay. So I wrote this out just to formally make the connection between induction and recursion. If you write down a recursive function in Disco, you don't have to write this whole thing. We could kind of do the same reasoning, but a little more concisely by just saying, look, it's defined for 0, and every time that we try to figure out what f of some number is, it calls f again, but with the argument that's one smaller. So if the argument to f is always getting smaller, eventually it's going to hit 0. So it's always going to be defined. That really is the same argument if you kind of squint. This is putting it a little more formally, using induction more explicitly. But when we say that kind of thing, like, oh, the argument's always getting smaller and eventually it'll get to 0, that really is a kind of an induction argument. Okay? And so let's see. Let's just look at some examples, or just to kind of see how this works. So f of 0 is 3, right? F of 1 would be what? It's 2 times f of 0 plus 3, which is so 2 times 3 plus 3, which is 9. Yeah, okay. F2 is 2 times 9 plus 3, which is 18 plus 3 is 21, right, and so on. Make sense? So I can, if I load this up in Disco, oh, what? Huh. So why did it not like writing that? Interesting. Okay. I don't know. Usually, right, in Disco you don't have to put, you can just put just put them next to each other and mean multiplication. But for some reason in this example it doesn't like that. I'm gonna have to look at that. I wasn't expecting that, but it works if we just we can put a multiplication sign. Right. And we'll just to make sure, right, f0 is 3, f1 is 9, f2 is 21, right? So this works just like we thought. And we could also, we could easily, for example, prove things about this function. And if we wanted to prove something about this function, probably we would use induction. Because the function is defined recursively, and so a proof by induction would fit very naturally. So we can prove things, or so we can also, we already proved something about f, which is that we proved that it was defined, right? But we could prove more interesting things. Also prove things about f using induction. For example, I claim that for all n, f of n equals, what is it, 3 times 2 to the n plus 1 minus 1. Not obvious. And actually we could check this. So one way we could check it, if we had made a conjecture, right? So maybe you calculated a bunch of values of f, and you kind of noticed this pattern. You said it seems like it's always 3 times 1 less than the power of 2, and so you kind of made the conjecture. But you could test it, right? You could say test for all natural numbers n f n equals 3 times 2 to the plus 1. I have to use a dot minus here because it's natural numbers. It says it might be true. I checked 100 tests and they all worked. So this might be a good candidate for us trying to prove it, right? On the other hand, if it had come up with a counterexample, then we're like, okay, well, it's definitely not true. So I'm not going to try to prove it. We'll do it. Right? Like maybe if we forgot the minus 1, or we did like 2 to the n. If we did just like got the this would be very easy to do, right? If you're like, it's 3 more than 1 less than a power of 2, but it's like, which power of 2 is it? I don't know, maybe it's 2 to the n. And it'd be like, no, that doesn't even work for 0. So, like, oh, I didn't do that, sorry. So, how would we prove it? Right, we prove it by induction. So, prove by induction. In the base case, well, f0 is defined to be 3, which is, if we put 0 in here, it's 3 times 2 to the 0 plus 1 minus 1. Is that true? 2 to the 1 is 2, minus 1 is 1, 3 times 1 is 3. So, check. In the induction step, we'll say, let n be arbitrary, and suppose that f of n equals 3 times 2 to the n plus 1 minus 1. All right, then f of n plus 1 is what? Well, f of n plus 1 by definition is 2 times f of n plus 3. So really, I should say that. Like this. So this is by definition of f. Well, we assume something about fn, right? So this is 2 times 3 times 2 to the n plus 1 minus 1 plus 3. So this is our induction hypothesis. And now we just have some algebra to do, right? So let's see. 2 times. Looks like it might be useful to do like. So this is like, okay, I don't actually need like these parentheses here because, so I can, this 2, I can distribute it over this. So this is 3 times 2 to the n plus 2 minus 2, right? So I just distributed the times 2 over this thing, plus 3. Let's see. Now I can factor out a 3. I have a 3 times something, and I just have a 3 here, which is 3 times 1. So this is equal to 3 times 2 to the n plus 2 minus 2 plus 1, which is indeed equal to 3 times minus 2 plus 1 is just minus 1. So that's what we wanted, right? Because f of n plus 1 should be equal to 3 times 2 to the, 1 more than n plus 1. Okay. I mean, the details of the algebra are important. You can go look at that later if you want. The point is, I wanted to prove something, some property that this function had, and because this function is defined for all natural numbers, and because it's defined recursively, it's very natural to use an induction proof to prove that. Because, the form of the definition exactly fits the way we do an induction proof, where we assume something about fn, and then we use that to prove something about fn plus 1. Okay, another example, we can say, we define Fibonacci numbers. So, we defined this the other day. We can define them in Disco this way, right? So you have the 0th Fibonacci number is 0. The first Fibonacci number is 1, and in general, fib, and the nice way to write it in Disco is to say fib of n plus 2 equals fib of n plus 1 plus fib of n. I don't have to mess with subtraction there. We can try this out. So fib of 1, fib 2, we can look at like the first 20 Fibonacci numbers. And it's kind of slow. 20 actually was probably too big. There. That does look like Fibonacci numbers. This is a nice way to define the Fibonacci numbers. It's a really lousy way to compute the Fibonacci numbers because it's extremely inefficient. But that doesn't matter. And why is this well defined? Well, the same kind of argument, right? We would say, we would need a proof by strong induction, I guess. We would say, well, it's defined for 0 and 1, and then for any, any number that's 2 or bigger, we assume that it's already defined for all the previous ones, so because it's defined for these, it's defined for everything. So I think it might be worthwhile trying to write down, or see like how can we write down a definition in Disco that's not well defined, and kind of what would go wrong if we tried to show that it is well defined by induction, right? So examples of recursive functions that are not well defined. So here's one way we could do that. So here's like bad 1. Bad 1 of 0 is 27, and bad 1 of n plus 1 is 5 times bad 1 of n plus 2. So anyone have an intuitive idea of why is this not a good definition of a function? Mason?
You're referencing something ahead of itself, so it wouldn't be able to compute because it would have reached that point.
Right. Yeah, I'm defining, so this bad 1 of 0 is fine, but then when I try to define bad 1 of n plus 1 in terms of bad 1 of n plus 2, right, that's only ever getting bigger. It's never going to reach 0. We think about it in terms of, if we try to prove by induction that this is well defined, the base case would be fine. But then we would say, well, suppose it's defined for n. Then we have to show that it's defined for n plus 1. Well, the definition for n plus 1 doesn't use n, it uses n plus 2, and we don't know anything about bad 1 of n plus 2. So we don't know if this is defined, so we can't say that this is defined. And so it wouldn't, the proof wouldn't work. And in fact, if we try to do this, I mean, I can say bad 1 of 0, it says 27. If I try saying bad 1 of anything else, it just goes into an infinite loop, right? So it is, it's calling like bad 1 of 2, which calls bad 1 of 3, which calls, it's just going to never stop. Here's another one. What's wrong with this one? Kind of obvious. But yeah.
There's no base case.
No base case, exactly. So it's not, I mean, this part looks fine. If it was defined in terms of n, if it was already defined for n, then it would be defined for n plus 1, right? But there's no base case, so it never kind of gets started. And in this case, we'll see, actually, if we try to run this in Disco, something else is going to go wrong. It's not going to go into an infinite loop. Does anyone have a guess what will happen? Try bad 2 of 7. Maybe this has never happened to you in Disco.
Because it would go to the negative, and natural numbers can't be negative, because it gives you an error.
Yeah, so it's going to be an error. It's not going to be an error about negatives because, we're never actually doing any subtraction here, right? But when it gets down to 0, basically, this definition doesn't apply when n is 0, right? Like, this only applies when you have something one more than a natural number. So we're going to get some kind of error. It's not a very good error, but basically it's like there was something where I was trying to pick the right the right definition to use that matched, the input. And I tried all the possibilities, and none of them worked. And so hopefully it could eventually make this error better. We'll tell you a little more about what exactly it was doing. It just tells you, yeah, something didn't match. But I mean, we can tell what didn't match is that this only tells you what to do for numbers 1 or bigger. It doesn't tell you what to do for 0. So this is here is recursive call is to a bigger recurse. One more thing we could do. Zero, dot 3 of n plus 2 is equal to dot 3 of n plus 1 times 1. No, let's not make it 0. That would be bad. Any ideas why this one is no good? Adam?
We didn't find n plus 1.
Okay, and why is that a problem? You're right.
Yeah. Well, it's it's obviously in the n plus 2 equation.
Yeah, I mean, there's actually a couple ways we could fix this. One way we could fix it is by putting a case for n plus 1. There's a different way we could fix it as well. This is actually related to, this is very similar to the problem that happened the other day when we were trying to prove something about the Fibonacci numbers. And we only put a base case for 0. Right? So this function only has a base case for 0, but in this case it's defined in terms of the two previous ones. Right? So in particular, it's not going to be defined for 1. Right? Because, well, this n plus 2 doesn't apply when you're 1 as your input. And since it's not defined for 1, then it's not going to be defined for anything else, because, like, well, 2 is supposed to be defined in terms of 1 and 0, but 1 isn't defined. So there's kind of not enough to get it off the ground, right? It needs 2 previous values on every step. And so we need to start it with at least 2 values that we just say what they are so that it can go in, right? So if we try this one, we're going to get a very similar type of error, I think, to the previous one. Yeah, it's the same error, basically. So not enough, basically. So yeah, we could fix it by saying, giving a case for n plus 1, but we could also just give say what bad 3 of 1 should be. Okay. Any other questions about those examples so far?
So, does that mean bad 1 can also be fixed if you give it 3 base cases, like 0, 1, and 2?
Which one? This
Bad
one?
1?
No. Because it's still defined, like, when it makes a recursive call, the argument's going to get bigger. So it doesn't matter how many base cases you give, it's never going to get to them because it's just like getting bigger and bigger forever. Yeah. The only way you can fix bad 1 is by deleting it and starting over. No, you could, maybe this was supposed to be n or something. If you made this n instead of n plus 2, then it would be okay. Matthew?
What if the base case was like a larger number?
You mean, if it was like, bad 1 of 10 equals something? Yeah, I mean, then it would be defined for, 1 through 10. It still wouldn't be defined for 0, and it wouldn't be defined for anything bigger than 10. right? So you can't, you couldn't fix it like for all inputs that way. Because there's no biggest natural number that we can define as a base case. So, probably if you're writing a recursive function, you're probably not going to make this mistake. It's kind of obvious in the code I do this. These mistakes, though, I've made these mistakes. These are very possible to do. If you just completely forget the base case, you're like, how can I forget the base case? Well, but imagine that it's a much more complicated thing, and you spent a lot of time thinking about, what this case should be, and you just forgot to say what it is when it's here or something. It's not that uncommon. This is even more subtle, right? Because you put a base case, but it turns out that you need two previous things, and so you actually need a two base case. So both of those are things that could pretty easily happen. Okay. So up until now, we've only been dealing with natural numbers. Right? Everything has been natural numbers. So we talked about induction. It was like specifically about natural numbers. All these recursive functions we've been defining have been functional and natural numbers. So the important part, I guess, in these examples is that they took natural numbers as inputs. We could have pretty easily made the outputs something different if we wanted, but everything we've talked about, to be able to apply induction to these so far, because the only kind of induction we know works on natural numbers, so, induction is actually more general than that. There's other things that we can define kind of using induction that we can define them using induction / recursion and prove things about them using induction and write functions on them using induction. So, recursively, we'll talk about recursively defined types. And before we get to an example of some actual recursively defined types, there's one or two other things about Disco that I have to tell you first. So, we've already seen Cartesian product of types. So just to remind you, so for example, or if A and B are types, then A times B is the type of pairs, like some element of A and some element of B, right? So, for example, I could have like full, right? Okay, so we know how to make pairs in Disco. It turns out, so this is kind of like multiplication on types. There's something that's kind of like addition on types that we haven't seen before. So this is the idea of disjoint unions. So if times is kind of like multiplication on types, there is also something that is like addition on types. Okay, and here's how it works. If A and B are types, then A plus B is the disjoint union of A and B. What does that mean? It means that values of type A plus B are So there's basically two kinds of values of A plus B. One is left A, where A is an element of A, or right B, where B is an element of B. So, how should we think about this? Well, maybe let's think about what it means that it's a disjoint union. So we've talked about union of sets before, right? And the way union works is you just like glom the sets together, and if they have any overlap, it just goes away. Like there's no duplicates. So if I have this set and this set, they share some elements. When I union them, like I don't have any duplicates anymore, right? But what if I said, well, I want to union these two sets. I want to combine them into one big set, but I want to remember like which element came from which set. I don't want duplicates to kind of get merged together, right? I want to say, oh, this is the two that came from that first set, and this is the different two that came from that other set, right? How would I do that? And this is called a disjoint union. The way to do that is that you can say, well, I'm gonna take each element from this set and each element from this set, and I'm gonna like attach a little label to each one. So like all the ones from the left set, I'm gonna attach a little left label to those. And all the ones from the right set, I'm gonna attach this little label right to those. And now I can tell things apart, because if I have like, if both sets had the number 2 in them, it's like, well, now I've got a left 2 and I have a right 2. And it's like, oh, telling me this 2 came from the first, the set on the left, and this 2 came from the set on the right. So that's what this is doing. So left and right are like tags or labels telling us which set of values came from. Does that make sense? Let's definitely do some examples. So, actually, let's just so for example, if I want to have something of type, let's say, n plus bool, what could be something of that type? So one thing we could have of that type would be if I say left, and then I have to put some natural number like left 3, right? This is yeah. And I can tell this is okay, because if it wasn't okay, it would have given me an error. So if I said like, for example, if I just say 3, this is not okay. This is not going to work, because 3 is a natural number, but it doesn't have type n plus bool. Everything of type n plus bool has to start with left or right. You can't leave that part off. So this is going to be an error, right? Because, oh, these don't match, right? One thing was a number, one thing was a plus. Was a disjoint union. So I could say left 3, I could say, left 7, any natural number I want, I can stick it in a left, and that'll make it have type n plus bool. Or I could say, right false, or right true. Okay. I could say, what if I say like n plus bool. So let's think about this. What would be some elements of this? Someone give me an example of something that would have type n plus z plus bool.
I'm not sure if it's the right syntax, but would you have right and then nested in that left, and then like
that?
Yeah.
Yep. So how does that work? Well, this first thing, the type is it's natural numbers plus something. Okay, so it's either going to be left with a natural number in it, or right with whatever the other thing is in it. So Matthew's saying, well, if we say right, and then the thing I need inside the right is something of type z plus bool. And that could either be a left with an integer, or it could be a right with a bool. Right, so we could say right, left. or we could say right, true. Could have that type. Okay? So, another way to think of this, you can think of the plus, it's kind of like or. Right? It's saying if you have an A plus B, then it means you either have an A or you have a B. You definitely have one of them, and the left or right tells you which one it is. A plus B kind of means A or B. Right? If we have a value of type A plus B, then we either have a value of type A, perhaps the left, or we have a value of type right and right. Okay. Any questions at this point? Okay, one more thing. There is also a type called unit, which has only a single value called unit. And you're like, well, how is that useful? We'll see. But, you know, I can say unit. Actually, it gets printed out as a little square. It also, it's like some Unicode square. And if I ask for the type, it says unit. Okay. So, kind of similar-ish to bool, right? Bool has only two values, true and false. So unit only has one thing. So you can think of bool as kind of being like the number 2, kind of corresponding to the number 2, and unit kind of corresponds to the number 1. Okay, so given that, we can start to do some interesting things with this. So I'm going to first define a list of, let's say, natural numbers. What is a list of natural numbers? It's either empty, okay, so it could be an empty list, or it's a natural number followed by a list of natural numbers. Maybe you've never thought of lists this way. This is one way we can define what a list is. So, you know, for example, like, you know, 3, 4, 5, that should be a list. So does that fit this definition? Well, it says a list of natural numbers could be a natural number, so in this case 3, followed by a list of natural numbers, 4, 5. So is 4, 5 a list of natural numbers? Yes, because it's 4 followed by a list of natural numbers. 5 by itself is a natural number followed by a list which is empty. So at the very end you just say and we can write this down as a Disco definition. So here's how I do it. So I can define my own new types in Disco by saying type, I'll call it n list, a list of natural numbers, equals. So we can define this as our own new Disco type. Well, if the list is empty, that doesn't really contain any information. It's just saying it just is a thing, the empty list. There's only one empty list. So I'm going to represent that by unit. So unit kind of represents the empty list. And the fact that this is an or, we want this disjoint union thing. Right? So a value, this is saying a value of type n list could either be a unit value, which to us we're thinking of it as meaning the empty list, or it could be something else. And what is that something else? two things, a natural number and a list of numbers. How do we pair up things in Disco? We use a product type, or a Cartesian product. So it's going to be a natural number times n list. So we could read this as a value of type n list is either a unit value representing the empty list, or a pair of a natural number and an n list. Okay, that's kind of how to read that definition. And hopefully you can see how that corresponds to how we were thinking about this. Is it making sense so far? Any questions? So let's rebuild this. Let's see if we can write down some, actually I'll just do it here, some example n list values. So, empty n list. So how would we write down the empty n list? Well, remember the empty list is going to be represented by this unit thing. But it's unit plus something. So to tell it which it is, we have to say left. Right? So I say left. And then, right, unit only has one value, which is called unit. So I can say left. So if I look like this, it should look okay. Yep. And then we'll say, example list. So if I don't want the empty list, I could instead say, no, it's not going to be the empty list, it's going to be this other thing. So I could say right. And now I have to put in here a pair of a natural number and an n list. Right, so, well, what number do we want first? 7, and then something. I can put whatever n list I want in there. So I don't know, what list should I put? Maybe I'll put, I could put left unit if I just want the empty n list, and then this would just then be a list with only one thing. But maybe I don't want it to be empty. Maybe I'll say, okay, the n list I'm going to have in here is going to again be a right value, which is going to have some number, let's say 2, and another n list, and maybe I'll say right again, 10, and then finally I'll say left. So you can kind of see how it is. It does kind of look like a list if you squint and ignore all the rights and lefts. We can load this just to see that it is okay with that, and yes, it's fine with that. So, yep. Okay, and let's write a function on lists. So, what function do you want to write? So we could like find the sum of the things on the list. We could find the length of the list. We could find the max. I don't know. But something else.
Let's try it out.
Max. Okay, sure. So list max. So this is going to be a function that takes an n list and returns a natural number, which would be the maximum number in the list. So find the maximum value in the list. Okay. Well, how's this going to work? So you know how we often, if we're defining functions on like, say natural numbers, we use, this is called pattern matching. I don't remember if I've used that term before. I hope I have, but where we kind of see, okay, what does the input look like? Does the input look like 0? Then I'm going to return this. Does the input look like 1 more than something? I'm going to return this. Right? So we're doing the same thing here. We're asking, all right, what does the input look like? And depending on what the input looks like, I'm going to decide what to do. What could the input possibly look like? Well, nlist is unit plus something. So the input is definitely going to look like either left something or right something. And that's how I can figure out, is it actually the case where it's the unit, which means the empty list, or is it the case where it's a pair of a number and a list? Okay. So if it's a left unit, I can also put underscore here for the unit because I know it's going to be unit and I don't care. But what should be the maximum value in an empty list? I mean, in this case, we can actually say 0. And I know you're like, I'm glad that you all are concerned about this because there isn't anything in the list. So like, what would it mean that it's maximum? But because we're dealing with a list of natural numbers, we can actually put 0. And that's going to be okay because anything else that's in there is going to be bigger than 0. Unless it's all zeros, in which case 0 is the right answer. But if it was a list of integers, for example, then we would really be in trouble because there's nothing we could put here that could serve as the maximum of an empty list. Okay, but then the other thing it could look like is it could look like right of some number, which I'm just going to call n, and another n list, which I'm just going to call, I'll call it L for list. Right? Well, what's the maximum of this? One thing I could definitely do, this L is an n list, so I could call list max on that. Right? And I kind of should expect that because since n list is defined recursively, n list is defined in terms of itself. Any function that we write on an n list is probably also going to be recursive. Right? So every time that you have an n list that uses an n list inside of itself, we're going to call the function on that. So I could call list max on L, and that would give me the maximum of like everything else in the list. But then I just have this one element n that was at the beginning. And I just want to ask which one was bigger, right? If this n is bigger than everything else in the list, then it's the maximum. Otherwise, maybe if there was something that was bigger over there, then that's the maximum, right? So I just want to say n. I think this is still the syntax of this in Discord. I kind of want to change it actually, but like max, you actually put infix, which is a little weird, but let's load this and try it. Yeah, so if I say list max of example list, it should say 10, right? Because 10 works. And if we wanted to prove that this function works, that it finds the maximum value, then we could prove it by induction. But we're going to have to wait until next time to think about what that means, because all the induction we've talked about so far has been on natural numbers, right? And this is not about natural numbers. This is on these endless things. So I think on Monday, I'll show you another example, which is we can make like a type of binary trees or something. And we'll also think about what does it mean to prove things about something like n list or like